Okay, we are on chapter 13. No, not 13. That's kind of like 13. Chapter 11. So last time we were talking about obviously the electron configuration. And remember, electron configuration basically tells us how the electrons are in the atom. And remember, there's really kind of two things that you need to know to write electron configuration. And that's the maximum number of electrons you could put into an orbital or a subshell. Remember, there's S, which could hold 2. P subshell could hold 6. D subshell could hold 10. F subshell could hold 14 electrons maximum. Again, you do not have to, fully fill them, but you can max them out with those. Also, remember the order at which electrons go into the atom is different than maybe you think about. Again, there is some differences in the energy of those. They always fill from lowest energy to highest. And remember, you can make that chart that we were using to basically on the paper yourself, but just remember basically 1, 2, 3, 4. Again, remember on the first energy level, that's where S's start. On the second energy level, so down a little bit to the right, is where P's start. On the third energy level, that's where D's start. And on the fourth energy level, that is where F start. And at that point, you can basically just fill in the numbers underneath with the same letters. And you could go to about 7 on most of them and you'll be in business in terms of that chart that we had. So, I mean, it's something you can make pretty quickly for yourself on paper here. And again, that will get you your proper order. And again, 3D, 4D, 5D, 6D, and 5F. And remember, we always start up out top. And again, you just kind of draw the lines and go kind of diagonal. And again, this is really where people mess up 3P. It is the 4S and then the 3D, and again, the 5S into the 4D and so forth. So you can recreate that pretty quickly on the page by just remembering basically 1, 2, 3, 4. And you can basically write any electron configuration you want. So again, if we had something like sodium, which is 11, we would start at the top there, 1s2, 2s2, 2p6, 3s1. We talked about writing electron configuration like so. There's also a shorthand as this is, that is 6, 8, 10 electrons, which is neon's configuration. So kind of a shorthand. You can put a noble gas in brackets and continue on the configuration as well. We also talked about orbital diagram, which is the arrows in sort of boxes. So if you're going to do that, you would have a 1s box, a 2s box, and because the p has 3 different orbitals, you'll 2p subshell there, and a box for our 3s. And remember that they go in first upwards and then down, up and then down. In a subshell like the 2p here, we actually go in one at a time and then we come back and fill them up going in the opposite direction. And in this case, we would just go up like so. Any questions on any of that there? All right, so continuing on here, we talked about a couple of exceptions to the normal electron configuration last time. And as I mentioned before, you are responsible for chromium and copper as the 2 exceptions that you should be familiar with. And again, the exception here has just been found to be more stable with, again, 1 extra electron up in the d orbital, 1 less electron in the s. And copper is the same deal. It basically has 1 more electron up in that D and 1 less electron in the S. But as I also mentioned, again, if you go on the periodic table there, below chromium and copper and sort of come in, there's a lot of those very similar types of exceptions that you will find. But for us, it would just be chromium and copper. For the other ones, you can write like normal, but be aware that there are definitely some exceptions in that area. So, if you're having maybe doing something online homework or something like that, and you get it wrong, you're like, I don't understand, and they're underneath chromium and copper, it might be one of those exceptions that you might want to kind of look up and see in the chart that's in your book as well. But as I mentioned before, you can see here something like PD actually has no electrons in the s. They've all been moved up to the d orbital. So again, there's a lot of exceptions sort of underneath there. But for us, just chromium and copper you're responsible for. This is what we would expect it to be if we followed our chart, but it's found experimentally to be more stable in this arrangement. In most cases, it's going to be more stable because of Hund's rule. It will basically kind of maximize those parallel sort of spins. The lanthanide series, which is on the bottom there, is where our F's start. Those two rows on the bottom are our F's on the periodic table. And we give either incompletely filled F subshells or cations that have incompletely filled F subshells. Once they're filled, we then go back to the 5D. So again, understanding that sort of zigzag is really important as well. Here is the electron configuration as I kind of see here, maybe on this one here. Again, you can see there's a lot of sort of those exceptions underneath chromium and copper along the way. And you can even see it here with platinum as well. So again, you'll see a lot of those sort of exceptions. Now, when we look at the periodic table has sort of groups that are based on electron configuration. So there are 7 periods which go left to right, obviously. And if you remember, N can have values of 1 through 7, N being the energy levels. And that's what those correspond on the periodic table. The first 2 groups on the periodic table represent the S's. And S's could hold 2 electrons, right? So like 1 and 2. Groups 3 through 8 is the P block. P subshell could hold 6, 1, 2, 3, 4, 5, and 6. D is the transition metals in here, and they could hold 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And F's down here on the bottom can hold 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So you can use the periodic table to sort of count off electron configuration if you sort of know what you are doing. But you do have to be a little careful, but let's just talk about a couple of them here. So let's just say we wanted to do sodium that we just did. So sodium is right about here. And we would start up here, and this is 1s2 down to here, so 1s2. This would be 2s2 to there. This would be 2p6 all the way to the end. And now 3s1. And you can count off the period, the electron configuration that way. If we were doing something like chlorine over there, which is number 17. So chlorine is somewhere right around here. We could do the same thing, again, starting up on top, 1s2 to there, 2s2 to there, 2p6 to there, 3s2 to there, and now this is going to be 3p1, 2, 3, 4, and 5. We could just count the boxes. I'll go underneath since I ran out of room there, but 3p5. So you definitely could count off electron configuration from the periodic table. You do have to be a little careful in certain spots. So for example, if we were going to look at like iron, which is right about there, I believe. We could do the same thing. This is going to be, again, 1s2, 2s2, 2p6 to the end, 3s2, 3p6. Now, the important thing here is this is 4s2. But what happens though right here is that is where the D start. If you remember, D orbitals actually begin on the 3rd energy level. So that is actually 3D, not 4D, even though it's on the period. It is 1 behind the period number because that's where D's start. And you can count it off, 3D, 1, 2, 3, 4, 5, and 6. And 3D6 would be the answer. So you do have to be careful here. That's 3D, as you can see here, 4D, 5D, 6D. The other place you have to be careful is if you get really deep down in there, anybody down here, this is actually 4F and 5F, and they do go right about here, and these guys are 2 behind the period number. So it does get a little bit kind of tricky there in the middle if you're not paying attention. But if you are and you understand that, you can use the periodic table to sort of count off electron configuration. Any questions on that there? So let's talk a little bit about electron configuration for ions. So when things do form ions, they're either going to form cations or anions. So if we take a look at our friend there, sodium, which is 11 that we just did, 1s2, 2s2, 2p6, 3s1. Now when sodium makes a charge, it will have a +1 charge. And when it has a +1 charge, it means it has lost electrons. That's what the positive charge means. So instead of 11 electrons, sodium with a +1 charge will have 10. And that means it will have a configuration of 1s2, 2s2, 2p6, or that is 10, which on the periodic table is neon's configuration. Now, if we have something that is negatively charged, let's say nitrogen here, which is 7 normally, it's 1s2, 2s2, 2p3 in this case. And when nitrogen makes a charge, it's going to be a -3, and that would also have 10 in this case. And it would end up with an electron configuration of 1s2, 2s2, 2p6, or that is neon. And that's a really important thing that occurs here, and we'll talk more about it in the next chapter when we talk about bonding, but that is the goal pretty much of bonding, is to reach the electron configuration of a noble gas, and that's what neon is. And in the case of sodium, it can reach neon's configuration by losing an electron. And if you look on the periodic table, what happens when an ionic compound forms, it actually goes backwards to the noble gas that comes before it on the periodic table, there in group 8. And if you look on the periodic table, what happens with guys that make negative charge like nitrogen is they go forward on the periodic table to reach the same electron configuration as a noble gas. They're said to be isoelectronic with each other. Isoelectronic are things that have the same electron configuration. So sodium with a +1 charge, nitrogen with a -3 charge, and neon are all isoelectronic with each other. They all have the same electron configuration. It happens for anything here that is a representative element. If you looked at calcium that has a +2 charge, calcium with no charge is 20 electrons, with a +2 charge will be 18. 1s2, 2s2, 2p6, 3s2, 3p6. R18 on the periodic table is argon, which comes again right before calcium on the periodic table. If you find calcium go backwards, you're going to find argon basically hanging out there. Now, this is what happens with representative elements, and these are elements that are not in the periodic table. They're elements that are not in the transition periodic table. They will, by again either gaining electrons or losing electrons, go forward or backwards on the periodic table and end up at a noble gas configuration. The reason for that is noble gases are chemically inert, they're super stable, and everybody wants to essentially become like them in terms of their electrons. It is important to remember that they do not become those elements. So this guy here is still sodium, and that is because it still has the proper number of protons. Remember, it's the protons that determine what element you have. So that sodium with a +1 charge still has 11 protons, which makes it still sodium, but now it has a much nicer sort of electron configuration, a much more stable electron configuration, because it has that kind of noble gas configuration. So sometimes people misunderstand when they do this and they reach that noble gas configuration. They sometimes think that they become that element, and again, they don't, because The only way for that to happen is to change the protons, and obviously we do not do that here. We're just changing the electrons. That's happening in this particular case. Now, what happens in the transition metal region? It is a little bit different for transition metals. What happens? So what happens with transition metals, let's just take our friend iron there, which is 26. We just did the configuration for. And basically here, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 here. Gets us our 26 electrons. We could shorthand this as up to here is argon. So that is argon 4s2, 3d6 on the shorthand. So what happens when a transition metal gets electrons into their atom is the order at which we talked about, which is the electrons will go into the s orbitals first because they are lower in energy, and then they will fill up that d. So we'll go one at a time basically, and back that way. Now, what happens with transition metals is they are very close in energy, these orbitals, the 4s and the 3d, for example. But what happens when we start putting electrons into the d orbitals, they actually switch in terms of their energy. And there is a switch that occurs. And after we start filling the d orbitals, what ends up happening is the 4s actually ends up being a little higher in energy than the 3D. And this occurs again after we start filling the d orbitals with electrons. And this affects how transition metals will lose electrons. Basically, things will lose the highest energy electrons first. So in the case of transition metals, that is always going to be the s electrons. So they will always lose those first. And then, if necessary, they can dig into the d orbitals and lose some of those if they need to. And that's why, as we'll talk about with naming, transition metals can make a variable type charge because they have all these kind of valence electrons available to them. So they can dip into kind of those d electrons. That doesn't happen with the elements on the side. For example, the metals in group 1 and group 2. Pretty much once you get rid of those highest energy electrons, there's not a good chance you're going to be able to remove any more after that part. So since these are all kind of considered valence electrons for transition metals, they're able to be lost. So if we took something like iron that had a +2 charge, instead of 26 electrons, it would have 24 as it lost 2. So what would happen in this case is it's actually going to be these two right here that are going to be lost first. And that means that when we write the electron configuration for iron with a +2 charge, it will be argon, and we're going to get rid of actually these first, and that will leave us 3d6. So argon d6 would be the proper electron configuration for iron with a +2. Now, iron can also make a +3 charge, which means instead of 24, it will have 23 electrons. Same thing is going to happen first is they're going to lose these S's. So these again are going to be lost, but that's only 2 electrons. So the next thing that happens is they can dip into the D and lose one of those. So we can then take one out of the D, and we will end up with argon 3d5. So transition metals are very different in that sense. They will always lose those s electrons first and then lose into the d if necessary. So the difference really is when you look at your electron configuration, for transition metals, it's not usually the very last ones that get lost, but it is definitely those S's that go first, and then maybe some of those last ones. When you look at everything that's not a transition metal in terms of a metal, they're usually just the last ones you wrote on your electron configuration or the ones that get lost. But basically, if we look here, all through the transition metal region, what happens when they do lose electrons is they will always lose these guys first, and then they dip into the D. So that's sort of the pattern on that. It's always kind of losing the S's first, and then they lose some of the D's if necessary. So why don't you try a couple here? Why don't you write the electron configuration for, I don't know, let's do sulfide. Let's do, we'll do potassium. Let's do nickel with a +4 charge. And let's do Mn with a +2 charge. So in case you can't see the periodic table, sulfur is 16, potassium is 19, nickel is 28, and our Mn here is 25. Okay, so let's take a look. Sulfur here with no charge would have 16 electrons. With a -2 charge, minus means it has gained electrons, and 2 is how many it gained. So instead of 16, it should have 18 electrons. Let's come down here. 1s2, 2s2, 2p6, 3s2, 3p6. That is 18, or that is argon's configuration. So again, if you look at the periodic table, sulfur moved forward to argon's configuration, which is what we expect to happen. Any questions on that one there? We take a look at potassium. Potassium with no charge is 19 electrons. Positive means it has lost electrons, and the one positive means that it now also has 18 electrons. Excuse me. Which means it will end up exact same place. 1s2, 2s2, 2p6, 3s2, 3p6 are again, it also reaches argon. Potassium backs up on the periodic table again to reach the noble configuration there of argon. So as you can see there, in terms of our representative elements like sulfur and potassium, we either kind of put it into the last one or they lose the last sort of electron or orbitals that are there. Nickel with no charge is 28. With a +4 charge is not 28, 24 in this case. So I'm just going to do nickel with no charge, which is 28. So nickel with no charge is going to be 1s2, 2s2, 2p6, 3s2, 3p6. Remember, 4s2 comes next. And then we'll go 1, 2, 3, 4, 5, 6, 7, 8, 3d8 here. So when nickel, which is a transition metal, loses those 4 electrons, once again, because of that switch in energy, we will lose our 4s first, and that is 2 electrons. In this case, it still needs to lose 2 more, so we will then dig into our Ds and take out the other 2. And this will give me, and I'm just going to abbreviate through here, that is argon's configuration. And we will end up with 3d6 in this case. And again, argon's configuration is what's underlined there. Yeah. Any questions on that one there? As you can see as well, transition metals do not back up to noble gases, and that's because they just have a lot of electrons to try to get there. For example, something like zinc would have to lose like 12 electrons to back up, and it doesn't usually happen. So transition metals don't end up usually in noble gas configurations, but representative metals, groups 1, 2, and aluminum there will end up at a noble gas. We look at Mn here, which is 25, no charge. So once again, I'm going to just do it with no charge first. And that's going to be argon, which will take care of my first 18 there. 3d5. I'm sorry, I missed the 4s2. Oops, come here. Went off a little too soon. 4s2 for this guy and 3d5. Once again here, going to lose 2 electrons, which means we'll have 23. So we will get rid of those guys first. Again, not the D's in this case. And we'll end up with 3d5 here. Or obviously you could write out the argon part as 1s2, 2s2, 2p6, 3s2, and 3p6. question on electron configuration for things with charges. Yes. All right, so clearly you need to be able to write electron configuration for neutral things, things with charges. Let's talk again here to finish out this chapter about some periodic sort of properties. And one of the first things we're going to talk about is valence electrons. And valence electrons are important electrons, as we'll definitely talk about in the next chapter. They are the ones that are involved in bonding. Valence electrons are the highest energy level electrons that you could have. So for example, if you look at your electron configuration for sodium, 1s2, 2s2, 2p6, 3s1. Remember that the front number is the energy level. So right here is our highest energy level. And this would be its one valence electron in the case of sodium. The lower energy electrons are sometimes referred to as core electrons. Core electrons are those lower energy electrons. They are closer to the nucleus, which means that they will be held tighter and not released as much. If you look at nitrogen's configuration, which is what's on the page here, 1s2, 2s2, 2p3. Again, first energy level, second energy level, second. So right here is the 5 valence electrons that nitrogen has. And these would be considered core electrons. So you can write out the electron configuration for everybody and figure out the valence electrons, but nobody wants to do that because there's a much easier way, and the number of valence electrons equals the group number. So the group number on the periodic table will tell you the number of valence electrons. So for example, if we look at sodium, that is group 1 on the periodic table, 1 valence electron. If we look at nitrogen, that is group 5 on the periodic table. And there it is, the 5 valence electrons. So if you just need to figure out how many valence electrons something has, the group number is the way to go. It's much quicker, obviously. You can just find it on the periodic table, figure out what group number it is, and you can basically determine the number of valence electrons from that. Now, when you look at the transition metals, we also can use the group number. And let me just go back here. We're at a periodic table, I think. Yeah, this won't work. Maybe. So if you look at the transition metals, it's a little bit different in terms of how we figure it out. We actually just kind of use the regular numbering. And what I mean by that is like this is group 1, this is group 2, and then this is 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we just kind of use the regular kind of 1 through 18 numbering when you're trying to figure out valence electrons for a transition metal. So for example, if we look at iron, which we did the electron configuration for a second ago, which is 26, that is argon, 4s2, 3d6. Right here is iron's 8 valence electrons, those S's, and again, the D's being available to them. We did like Mn, right? And again, that was argon, 4s2, 3d5, and right there is its 7 valence electrons. So because the transition metals have those S's that are considered obviously valence electrons, and they also have the d orbitals available to them. If you just do kind of the regular left to right 1 through 18 numbering, especially just for the transition metal region, that's where you would want to use those numbers for valence electrons. The good news is we really don't do much with transition metals in terms of bonding and things of that nature. So a lot of times you don't have to really worry too much about how many valence electrons they have. But in case you do come across a question, that's how you want to number basically 3 through 12. And as I was mentioning before, essentially something like zinc has 12 valence electrons, which means in order for it to back all the way up to argon, it's got to dump all 12 of those electrons, which is never going to happen. So that's why, again, those transition metals, because they have a lot of those electrons available to them, especially some of those d electrons, they typically won't end up at a noble gas configuration because it's just too many to lose. It's not going to really happen. All right, so that is valence electrons there. Now, when we talk about metals and nonmetals, and we saw this with that experiment we did last week, um, when we go down a group, metals typically give up their electrons a lot easier. And because of that, they become more reactive, really. And if you remember when we were talking about it, and what we saw, for example, in those videos in lab, was reactivity, for example, in group one increases as you go down the group. And that's where we find our most reactive metal. If you look on the periodic table, lower left of the periodic table is where our most reactive metal is. And that's because they are pretty much easy to give away electrons, and that's going to make them pretty reactive. When we did the halogens, where the different layers change colors and all that good stuff, what we saw is in group 7, right, reactivity increased as you went up group 7. And what we find in terms of the periodic table, most reactive nonmetal in the upper right of the periodic table. Now, some of the reasons why that happens is some of the things we talked about in lab. So we're going to officially talk about some periodic trends which account for why we do see those reactivities being in those locations. So let's talk about a few things. We might have touched upon it there in that lab last week, but the first thing is effective nuclear charge, which again is Z effective. And effective nuclear charge is, again, if we kind of look at a pretty straightforward example, which is lithium, 1s2, 2s1. Lithium is group number 1, which means this is its valence electron, and this is its core electron. And if we just kind of look at lithium, again, it has a positive 3 charge in the nucleus because it has 3 protons. And we do have 3 electrons. We have 2 of these kind of lower energy electrons, and we have our valence electron. I'll just kind of put in parentheses out there, which is our valence electron. And these will be our core electrons. And as we might have talked about it previously, when we think about our core electrons here, they're pretty much right up front. They're pretty close to the nucleus. So they're going to feel pretty much that full strength of that positive 3 charge. So that's something we talked about, the electrostatic attraction, the attraction between a positive charge and a negative charge are related to the size of it. So the larger the positive negative charge, the stronger those things are going to be held together. So those core electrons are really going to feel a lot of that positive 3 charge, and they're going to be held really tightly. That is why, for example, core electrons, one of the reasons why core electrons are not involved in bonding, because they're just held so tightly, they are not going to find themselves leaving the atom. They're going to be held onto by the atom. But what happens with our valence electron when it is on the outside here is it experiences what is known as shielding. So this valence electron experiences shielding. And what is happening in this case is that valence electron is shielded by those lower energy electrons from the full force of that positive 3 charge. So that outer electron, because these other electrons are sort of in the way, doesn't feel the full brunt of that positive 3 charge coming at it. You could actually calculate it, again, and this is Z effective, is the positive charge of the nucleus minus the number of electrons that are in lower energy level, which in this case is 2. And effectively, what that outside electron, that valence electron, is actually feeling is a +1 attraction to the nucleus, which is a much weaker attraction than the full +3 attraction that those core electrons are holding. And that is why that valence electron, for example, can be lost a lot easier than those core electrons. It still feels an attraction, but is not held as tightly as those core electrons are. So it allows it to be easily removed. And that's essentially what a lot of valence electrons feel, is a much lower positive attraction to the nucleus than lower energy electrons do, just for the process of them being further away and things in their way of filling that. When we look at the periodic table in terms of Z effective, as we go this way, it increases. As we go this way, it decreases. As you go to the right on the periodic table, you're also increasing the atomic number, which means the nucleus will have a greater positive charge. So even though the outside electrons are feeling less of a charge, the overall positive charge to start with is larger, so they're still feeling a more attraction than the guys to the left. Another important sort of trend is ionization energy, as we talked about last time in lab, I think. Ionization energy is the energy needed to remove an electron. And when we remove an electron, we essentially make cations. So a lot of times we think of ionization energy as the way that we get to cations. And electrons are actually lost one at a time. So again, if you had something like magnesium, the first thing that would happen is magnesium would lose one electron. And that is what is known as the first ionization energy. Then magnesium that has already lost one electron will then lose a second electron, and that is known as the second ionization energy, and so forth. You could kind of continue the pattern down if you like. And we could lose a third electron, and that would be the third ionization energy. So each electron comes off one at a time, and there's a certain amount of ionization energy required to remove each electron. Every time we remove an electron, what happens to the size of that ion is it gets smaller because we lose an electron, so electron density shrinks, so everybody is brought in closer. And when that happens, when you go from like your first electron to your second electron to your third electron, you keep kind of bringing everybody in closer to that nucleus. So what ends up happening is it gets much harder and harder to remove electrons after you start removing one. And that's because the electrons that are left are now finding themselves closer to the nucleus. So when we talk about kind of the first ionization energy versus the second versus the third, it actually increases. So this guy would be the smallest, and then it gets larger every time you keep trying to pop off an electron. In general, what we see in terms of ionization energy is for the first ionization energy, which is that first electron that comes off, it increases as you go up to the right on the periodic table and decreases as you go down and to the left. So it gets much harder to remove electrons from the right-hand side and up than it is as you go down and to the left. And that also has a little bit to do with effective nuclear charge. Again, those guys on the right-hand side of the periodic table have more protons. So those outer electrons to start with, because of the larger positive charge, are closer in to the nucleus and held tighter, and it becomes harder to remove. And that's the general trend as we see. And here's a chart of actually the numbers. And for example, we take something like magnesium. Magnesium typically will only make a +2 charge. And that's because when we look at the electron configuration for magnesium, it only has 2 valence electrons. So you can see on magnesium, to remove the first electron is about 735. To remove the second electron, you actually double it. It's about 1400 joules of energy or kilojoules of energy. But once we get rid of those 2 electrons, we're now into our core electrons. And you can see a fairly big jump. It's almost 6 times the amount of energy to try to do that. And it's not going to really happen in that case. And that's why something like magnesium will basically top out at a +2 charge, because that's all the valence electrons you have. At that point, you've lost 2 electrons. The size gets smaller. Those outer electrons and those core electrons are even closer to the nucleus, and they're going to be held a lot tighter. Same thing with sodium. If we look at sodium that we saw before, 1s2, 2s2, 2p6, 3s1, that's obviously sodium with no charge. When it loses this 1 valence electron, it's 495, and then it's almost a tenfold jump to try to get rid of some of those core electrons. And again, under normal situations, that's not going to occur. And that's why sodium will always kind of top out there at a +1 charge and not be anything other than that. You could actually see an even bigger one here. Aluminum typically will make a +3 charge, which means it will lose 3 electrons. First one's like 580. Next one is a little bit more there, 1800, and then 2700. And at that point, once you lose those 3 electrons for aluminum, you then be in its core electrons, and it jumps all the way up to 11,000, and that's never going to happen under normal conditions. You're never going to be able to pull that electron off. It's just not energy efficient to do so, and that's why something like aluminum, again, will end up with always a +3 charge. So this is part of the reason why there are certain things that have fixed charges, because just the energy demand to try to remove more than those electrons is too much based on ionization energy. Now, electron affinity is basically the energy change that occurs when somebody gains an electron. So this is the energy change when we gain an electron. And that is typically what we think about as anions. Those are typically the guys that gain electrons. And if you have an affinity for something, that means you like to gain electrons, right? So if you have a high electron affinity, that means that you are pretty good at gaining electrons. And when we look at the periodic table in terms of electron affinity, it increases as you go up and to the left and decreases as you go down and to the right. It's not a perfect trend, but that is generally what happens. As you go up and to the right, they're much better at gaining electrons than they are as you go left and down on the periodic table. Another important sort of one that's sort of related to this, but is not the same thing, is electronegativity, which we'll talk more about in bonding. And electronegativity is, again, the ability of an atom to bring electrons towards itself. So electronegativity is the ability of the atom to actually just draw electrons near it. Electron affinity is actually the ability to gain electrons, how good you are at gaining electrons. So they kind of go in the same sort of orientation. As you look on the periodic table, electronegativity increases as you go up and to the right and decreases as you go down. Fluorine is the most electronegative element you could have on the periodic table. It's as far up and to the right as you can go, except for our noble gases, which are chemically inert. They're stable to begin with. They're not really looking to gain or lose electrons. Everybody else is trying to be like them. The last sort of trend that sort of ties all this together is as we go kind of up and to the right on the periodic table, the atomic radius basically decreases. So on the periodic table, as we go up and to the right, the size gets smaller. And as we go down and to the left, the size gets larger, actually. So we talked about it previously that if we have a neutral atom and it becomes a cation, it will typically become smaller, right, in terms of its size. And that's because it loses electron density. If we have a neutral ion and it becomes negatively charged in an anion, it actually becomes larger. So when somebody gains electrons, the opposite occurs. They actually gain more electron density, and the size of the anion gets larger because there's more electrons in there, so the overall size gets larger. In a neutral atom, this again is the trend that we see on the periodic table there. It increases as you go down and to the left and decreases as you go up and to the right. So if we look at atomic size, as you can see here, and if we put on this periodic table all the trends that we just talked about, which is something like Z effective increasing this way and decreasing that way. We have ionization energy increasing this way, decreasing this way. We have electron affinity increasing this way and decreasing this way. We have electronegativity increasing this way and decreasing this way. If you take all of these sort of trends together, what happens when we come up to the upper right of the periodic table, we have all these trends of I am smaller, I'm going to hold on to my electrons a lot tighter because I have high ionization energy. I also have very high electronegativity, which means I'm going to hold on to my electrons and also want to kind of take yours as well. And all of those trends come together to know what we know about nonmetals, which is they typically like to gain electrons and become anions or negatively charged. If you look on the opposite end over here to the left and down, where we have metals, they have all the opposite properties. They're really big, which means their outer electrons are not going to be held as tightly. It doesn't take a lot of energy or convincing for them to lose electrons. They have no interest in gaining electrons. And all that put together is why metals typically like to lose electrons and become positively charged ions in this case. So all of these sort of trends are the reason why um, nonmetals sort of gain electrons, metals lose electrons, and that's also why we'll talk about here in bonding why an ionic compound forms between those two things. So when you put a metal and a nonmetal together, you have the perfect situation of the metal's going to get rid of its electrons, nonmetal's looking to pick them up, so we're going to get that transfer of electrons. And when you think about the other type of bonding that we'll talk about, which is when they share electrons, that happens when we put two nonmetals together. So when we put two nonmetals together, both of them have the same characteristics of I would like to keep my electrons, I would like to keep my electrons, so we'll just kind of share electrons in that case. And it's really the basis for why we see different types of bonding. Any questions on that there? All right, so let's take a look here. Oh, there's the answer, but let's take a look at why that is the answer. Which one should be the larger atom? That's sodium and chlorine. Obviously, sodium and chlorine are in the same period on the periodic table. So we got sodium all the way over here to the left and chlorine all the way to the right. And remember, size decreases as we go to the right on the periodic table. So sodium should be larger because of that. When we look at lithium, cesium, which one should be the larger one? This one should be, we look at the periodic table, we have lithium and we have cesium in the same group, and size increases as you go down the group. They're both there in group one, and we should have cesium as our larger atom in this case. Which one is a larger orbital there? The hydrogen 1s orbital or the lithium 1s orbital? The hydrogen is a larger 1s orbital, and that's because of the positive charge of those nucleuses. Hydrogen has one proton, which is a +1 charge. Lithium has three protons, which is a +3 charge. So when we talk about our 1s orbital there, remember the attraction between charges increases with size. So because this is only a +1 charge, it does not pull in as close as what's going to happen with the 1s orbital here in lithium. That 1s orbital is going to feel a much stronger attraction to that +3 charge and going to be pulled in closer. The end result of that is the overall size of the hydrogen is going to kind of be a little bit bigger as well. And in terms of lower in energy, it's actually going to be the lithium in this case. For this reason, it is going to get pulled in closer to the nucleus, which means if it's closer to the nucleus, it's lower in energy. And that's what we're going to see in that particular case. Any questions on those two? So we want to arrange these in increasing ionization energy. So if we look on the periodic table, sulfur, oxygen, and fluorine is their arrangement on the periodic table. And if we're looking at ionization energy, again, it increases as we go up and to the right and decreases as we go down and to the left. That means in this particular case, we would be increasing in this direction. So we want to go from lowest to highest. So increasing up and to the right. So it should be as it is there. Sulfur, oxygen, and fluorine is the proper order. When we look at atomic size, is the only one that decreases as you go up and to the right and increases. Everybody else is the opposite. And in that case, basically, as we go up and to the right in terms of atomic size, we're decreasing. So it should be fluorine, oxygen, and then sulfur in that direction. Any questions on that there? Okay. And that is chapter 11 here for today, I think. All right, we're going to lay it up there.